All right, so now we're going to look at section 4.8, and this is where we're using regression models. All right, so a regression model is a function that describes the relationship between an independent and dependent variable, x and y, time and position, things like that. Independent, the value you can plug into. Dependent, the value whose value is dependent on the independent value. So that's going to be your output value. Typically we talk about independent being your domain, dependent being your range. All right, and it's given by two or more variable data set, usually found with technology. All right, the types of regression models that you're going to look at are going to be linear, quadratic, and exponential. And it's chosen by the user. You can look at a situation of points and you can get an idea of what's going to fit it best. And these are not the only ones that you can do. You can do very, very complicated ones. Matter of fact, in calculus, you actually end up doing a thing called a Taylor polynomial that not only goes linear, quadratic, cubic, quintic, but you can have any degree that you want to, and you're coming up with a polynomial that is going to approximate over a certain domain. It's going to be very, very accurate for that group of points. We're not getting that deep into this. The model is chosen by the user depending on what the points look like they're doing, and the model is considered appropriate if the graph of the residuals appears without pattern. And the residuals just mean what's left over. So the residual value is the difference between the actual value and the value predicted by the model. So it's the part that's left over. So if your residual graph doesn't have any kind of pattern to it, that means that you don't have a set amount of error that is increasing or decreasing or changing in a set way. Therefore, if the residual value graph has no pattern to it, then you're predicting it pretty well. Now you can be away from the actual value, but as long as it's scattered out all over the place and not really within a pattern of getting more and more and more away from the value in the positive, or more and more and more away from the value in the negative, then you've got what's considered a decent regression model. All right, so data for a random sample of high school students is shown by the scatter plot. So this is the data for every one of the absences. For every number of absences that a student has, they put a point on here at what their GPA was. So describe the relationship between the number of absences and the student's GPA. Well, understand, when you look at these pieces of information, when you look at these scatter plots, it is not going to be a linear expression typically. There's going to be things that are scattered. You're not going to have someone with 40 absences that has exactly the same GPA across the board. So there's going to be some that are smarter with 40 absences. There are going to be some that are not smarter with 40 absences. So the GPA is going to range. But what you're looking for is you're looking for a general form of what's happening. And if you do that, you can kind of see that they're all going in that big column of information. And what it means when we describe the relationship, we can see as the number of absences increases, the student's GPA decreases. So remember, as we're going in this direction here, the number of absences is going to increase and our GPA is falling as a group as we go back and forth, as we go towards the right there. Now, if we're looking at just 2 or 3 points, well, I mean, we could literally go in here and we could draw a line across here and hit 2 points and say, no matter how much the absences increase, we have no change in GPA. But that's not true, because you have to take the entire set of data. So you have to look at the entire range of data that we have here, and here, and here, and here, and here, and what's happening with that range. That range of data, although it's spreading out a little more, but it's also decreasing. The entire range is going down as we go to the right. So does this data seem to suggest a linear, a quadratic, or an exponential model? Well, if I were to go in here and try to fit a model to this, I'm thinking I would get right in here in the middle, and I would probably do, if I could draw a straight line, it would be awesome, but I can't. But that's what I would do, would be a linear. So this is going to fit a linear because the group fits a linear. So linear because the points fall into a column, and there doesn't seem to be a curve. So we're talking about that going straight down as we're going left to right. And if we were doing this and there was a curve to it, well, then you're looking at in the middle of those points, there would be a curve to it in some way. Like if it did something like this and there were points up here and down here and these points weren't there anymore. But we don't have that situation. All right, and number 3, a least squares regression model for this data is given by y equals 3.53496 minus 0.0146x, where x is a student's number of absences and y is the student's GPA. So what they're saying is that this is the equation that is modeling, that is approximating those points that we saw in the previous graph. So this is the residual plot. Use the residual plot to determine if a linear regression model is appropriate. Well, as we look at this, what we can see is this thing's scattered out all over the place. There are just as many above as there are below, and we've got, what we're talking about is the zero line. There are just as many above the zero line as there are below the zero line. And it's almost on like a one-to-one thing. There's not a certain pattern that's taking it off in this direction or taking it off in that direction. So what that means is that our error, how much we're away from the actual value, is not increasing in a big way as we get further and further out with our data points. So they're staying about the same amount away from the approximated value that's approximated by this equation. So if that's the case, and we're not getting these huge values where we're off by, an amazing amount over and over and over and over again, either positive or negative, then that means the model is going to be appropriate. So is a linear regression model appropriate? Yes. There is no pattern. In the residual plot. And the residuals look randomly distributed. So we could imagine that this 0 right here are and no, we're not imagining, it actually is. Those would be the values that this equation up here that we were told is modeling that would get. For 0 absences, we would have this value, whatever it might be. And those are exactly the values that this equation right here spits out. And this is how much the residual, remember, is how far away from it is. So we're calculating those values, and then we're looking at the data points that we had in that previous one. And for each one of those data points, what we're going to do is we're going to go in, we're going to subtract the value that we get from the approximation, and then we're going to plot that difference on here as a point. So in other words, when we get to 0, we had 2 points maybe. I don't remember what that graph looks like, but we have 2 points that are close to 0 and a little bit more as we get further to the right. But what we would do is we would end up finding that we've got a linear expression that is this equation right here. If we graph that line, it's going to be this far, there's going to be one point that's going to be that far above it and another one that's going to be that far below it. And then that's all this graph is it's telling how far above and how far below each one of those points is away from this equation right here, the linear expression of that equation. So as long as you've got roughly the same amount on top, roughly the same amount on bottom, and there's not a big swoop to get away from the 0 line, either positive or negative, then our approximation is pretty good. And that's the case here. We've got some that are above, some that are below, but it's equally distributed pretty much. It's not exactly equally distributed, but it's close. So that is not a bad regression model. All right, interpret the slope of the regression model, okay? So the slope is negative 0.0146. So 0.0146 negative is the amount of GPA value lost per absence. All right, so 0.0146 is the amount of GPA value lost per absence that is predicted. I should put that in there. That is predicted by the equation or by the regression equation. All right, so let's do number C, or part C. Use the regression model to predict the GPA of a student who has 23 absences. So that means we're looking at Y of 23, and that just means we're just going to plug in 23 for our X. We got 3.53496 minus 0.0146 times 23. And then, of course, we would punch that in our calculator. And we end up with a GPA of 3.19916. So that's the whole purpose for having a regression model, is you can plug in values and you can approximate what you expect the value to be for other values that you may not have actual numbers for. You know, we may not have had a number in here where we had exactly 23. It looks like we may, but that the regression model is used to approximate what it's due, to look for trends and things like that. All right, hope that helped a little bit.